Okay, so today we're going to derive the relationship between Young's modulus of an object and its interatomic spring stiffness or constant. We know for an object, Young's modulus is given by stress over strain, where stress is force over area and strain is change in length over length. Now in our case, let's suppose we have a wire. The wire has a length of L and a cross-sectional area of A, and it has a mass of M hung to it. So then wire has an atom, and each atom has a length of D, or we can say the distance between two atoms in center is D. So there are two forces acting on the wire. One force is the force due to earth, mg, and the next force is the force due to spring. And the force due to spring is given by K times delta L, where K is the spring stiffness of a wire and delta L is the change in length. As we know, where the mass is hung to the wire, it changes the length by delta L. Now these are some of the variables that we have defined in this case. A is the cross-sectional area of the wire, L the length, M is the mass hung to it, delta L is the change in length, and D is the length of each atom, D squared is the area of the atom. Now Kw is the spring stiffness of a wire as a whole, and Ks is the interatomic spring stiffness, Y Young's modulus. Now we are interested in defining the relationship between Ks and Y. Now we know for a wire with a mass, the change in momentum in Y direction is given by F net delta T. F is force due to spring minus force due to earth mg times delta T, which is 0. Now this gives us Kw, which is the spring stiffness of a wire, not this interatomic spring stiffness, as mg over S. In our case, S is the change in length, which is delta L. Now, in a wire, we know that there are small springs in series and small springs in parallel. Now when the springs are in series and they're connected, they stretch twice. That means they become weaker. And when they're in parallel, the parallel springs are holding this same mass. So their interatomic spring constant increases and they become stronger. So effective spring constant will be half for springs in series. Now, after knowing that, we can write that total spring constant of our wire as total springs in parallel divided by total springs in series times interatomic spring constant. Now to find the total spring in parallel, we take a area of wire, and the area is given by A divided by the area of each atom, which is D squared. So NP is A over D squared. Now to find the NS, the total number of springs in series, we take the total length of wire divided by the total length of each spring, which is L. So total number of spring in series NS equals L over D. Now plugging these values in here, we get our Kw equals A over D squared L over D times Ks, where Ks is a interatomic spring constant that we're interested in. With solving this, we get A over D squared L over D, D and one of the D's cancel, so Kw equals A over D times L times Ks. Let's say this is our second equation. Now in here we had our first equation where Kw was equal to mg over delta L. Now we can equate these two, and when doing that we get mg over delta L equals this part A over dl times Ks. So on moving things around and making Ks alone, Ks will be equal to mg divided by delta L divided by A times D times L. Rearranging, we get F over A delta L over L. Now F is same as this mg as we defined earlier. So force upon this area, and delta L is here, and this L comes down and D stays here. Now we know force upon area is a stress, and the change in length over length is a strain. And as we had defined earlier, using this formula for Young's modulus, this part right here is our Young's modulus. Therefore our Ks, interatomic spring constant, will be equal to Young's modulus times the length of each atom. So this is how we can define the relationship between interatomic spring stiffness and the Young's modulus. So Ks is equal to Young's modulus times D. Thank you.